So hello everyone, welcome back to our day 3 advanced data visualization with ggplot2 workshop. And I'm Wenbin, and this is our final day. So we are going to finish all the teaching materials today. And in the past of 2 days, we have already go through the data visualization basics, specifically know the structure of ggplot2 and also learn how to do some data wrangling, data cleansing in the tidyverse package suite. And then in day 2, we use the ggplot2 to build some plots layer by layer, specifically explore the different plot types, basically like some line plot or scatter plot, etc. And we also talk about how to getting more control on the plots by setting the scale or setting the coordinate system. And this is our day 3. So our day 3's main focus will be some examples and also the useful packages. But before we do that, we need to wrap up the themes and the legends, like how to getting more control on the non-data ink. So for today's workshop, as we mentioned, we are going to learn the legends and the themes, how to set them, how to customize them, and then we will move on to some kind of principles of data visualization. And in the R Markdown file, we will go through some useful examples and also the useful packages. Basically, those packages are well designed and they are specialized in some way to help you getting the data visualization more efficiently. So this is a 3-hour workshop. We are going to have 10-minute break every 45 minutes. And in the last session, we will have 30 minutes. And then the rest of the time will be practice and the Q&A. So for those of you who take the workshop for course credits, so you are going to have a homework assignment, and the homework will be released on the weekend. You will have 2 weeks to finish them. So basically, I will try to give you some examples, like give you some example figures, and you will do your best to reproduce the figure. So basically, you can use a lot of online resources, for example, the ChatGPT, or even search the Google to find how to make the plots. And because this is a graduate level course, our main goal, our major purpose here is to learn something that you don't understand before. So we are not going to give you a very hard time. Like we are not going to give you a very hard homework that you probably will going to spend 10 hours to finish one problem. We're not doing that. So basically those homework will be really similar to the examples we work on in the workshop, and it should be kind of easy to solve. So the major goal of the homework is to help you to review some of the contents and learn the materials better. So before we move on to the study new things, I still want to do some quick summary about what we have done so far. Specifically in the day 1 and day 2, we talk about the grammar graphics. So this is actually the foundation of ggplot, and by mastering each of the component, we basically master the ggplot usage. So in the day 1, we see this figure before that there are several different layers, different components of the ggplot. Specifically, the data is the source of the plot. Aesthetic mapping defines how we want the data variables mapped to the aesthetic variables, and the geometry help us to render the plot, whether you want to plot the data using a scatter plot, using dots, or using some other bar plots, etc. And the fastest is helping us to split the data into different panels and make a plot for each panel. Statistics is doing some statistical transformation. For example, using the geom smooth, we have done it yesterday tries to fit a linear model or noise model, etc. So basically, it gives us some summaries about the data itself. And the coordinates defines the plotting space for the data. And for the sim, which is we are going to learn today, is that we describe all the non-data ink. You want to customize your color of the plot, the background, etc. Basically, we are going to finish that using the sim. So this is the syntax of ggplot2, and basically you can clearly see the correspond with this the left panel picture well, that you have the data, you have the aesthetic mapping, you have the statistics, and also some coordinates, facet, scale, sim, etc., etc. Basically, this is just like how ggplot2 designed. It's basically designed based on this figure. So for the data, for the very first thing, we learned that talk about the variable types, factors, and the data frame, and also go over a lot of the data wrangling functions. So basically, every row is a variable, and every row is an observation, every column is a variables. So we have functions to manipulate the observations. We have functions to manipulate the variables. So this is usually very useful when you are working in the R and doing some data processing work. And also we have the reshape tries to convert the data from long format to wide format or vice versa. And we can also summarize the data to get some kind of statistics. For example, you want to calculate the group mean or even the group variance. You simply group by the variable first and then summarize by specifying the functions you want to use, like a sum or the mean, or even the SD stands for the standard deviation. And lastly, we talk about the pipe that we can chain all the functions together. So this will make our code look nicer. So after the data part, we learned the aesthetic mapping, which describes how the variables are mapped to the visual properties. So in the right panel here, we listed the different visual properties, like the positional properties, like X and Y, and the color, the shape, the line type, labels, etc. So basically, to specify the aesthetic mapping, you simply input the value and the name pair. So here, X equals to the log displacement. So basically, just put the pairs inside. Then we are done for this part. We also talked about the geometry yesterday, that there are some basic geometries like the line geometry and also the region geometry. For the line, we talk about how to make a curved line, how to make a straight line based on the starting point and end point, how to make a straight line based on the slope and the intercept, and also how to make the collect the different observations using the geometry path or geometry line. For the region, we learned how using the geometry rectangular to draw the rectangulars. And if you want to plot more complicated shape, you can use the polygon. And the geometry ribbon tries to draw a path with a vertical thickness. So for the one variable type of figure, we have the we can use different plots based on the variable type. For example, if it's a discrete variable, we can use a geometry bar, which will display the count distribution of the discrete variables. So it specifically will do some counting first, and then plot for each of the category what's the occurrence of this variable of this value. For the continuous variables, we can use the 4 different plot to represent the distribution. Usually we use the geometry histogram or geometry density a lot, but there are also some other like a frequency poly to plot the distribution and just collecting them using a line. And the density is a more smooth version. based on it, we'll do some local density estimation first. And the dot plot tries to stake the points into to represent the distribution. For the two variable type plot, if the two variables are both continuous, we usually use a geometry point to make a scalar plot. And based on this scalar plot, you can actually add some additional layers. For example, the geometry smooth, try to do a fit, like run a least square regression, or even run some generalized linear model regressions. For example, the logistic regression, etc. The geometry quantile will try to plot the quantile regression, and the geometry rug will display the marginal distribution. And if we have the one continuous variable and one discrete variable, so which is usually the we see this many times in our real data or our own research, that we have different groups, which is a discrete variable, and we have some kind of measurement, for example, the gene expression or some kind of DNA methylation, etc. So it's a continuous variable. So basically, we can use the geometry of box plot, Bell-Ning plot, or bar plot to represent them. So the box plot will display the different quantiles in the data. Bell-Ning plot will display the whole distribution, and the bar plot will display a bar chart of some pre-computed summaries. So specifically, the geometry bar, the default statistics is the count. So if we want to use it on the continuous variable, we should use the stats identity, that we will not do the default counting, but just use the value in the continuous variable. And also, if we are facing the overlapping issue of the dots, we can use the geometry data. So basically, this will add some kind of random noise on it, which will make the plots have less overlap. So there are also some other categories, like a three variable. We can plot the geometry using the geometry contour to display the contour plot, and using the tile to plot a heat map. And for the 2D distribution, we can use the bin 2D, which will summarize the data into different bins. And for each bin, it gets represented by a rectangular. The hex will use the hexagon as a representation, and we can also estimate the 2D density. This will give us a smooth version of the 2D distribution. And for the uncertainty part, we can use the crossbar, arrow bar, or even the point range, etc., to represent the mean and also the standard deviation for each of the observations for each of the X. So after the geometry, we also briefly introduced some statistical transformation, but because we don't use it that often usually, so we didn't dive into too much. But basically, it's pretty kind of we already get in touch with it using some of the geometry part. So each of the stats function, they have some kind of alternative form. Basically, you simply specify the stat to be some value in the geometry. For example, if you want to count the bins, you specify the stat to be bin. It will try to bin the values, continuous values, and do the counting. And for example, if you want to do a contour plot, you specify the stat to be contour. And if you want to do some kind of fitting, you specify the stats to be smooth. And if you don't want to do any operations, specify them to be identity. So this is what we saw before about the geometry bar using with the continuous variable. So after that, we also talk about the position adjustment. So this is sometimes quite useful to reduce some overlapping. For example, here we don't see if your data has a lot of a lot of ties in the values, so you cannot tell on the plot whether this represents one single dot or it's multiple dots overlapped together. So basically, you can use the position adjustment functions. Position nudge tries to move the points by a fixed offset. Position theta will add a random noise, and you can specify the seed within the getter so that every time you run the code, you always end up with the same plot and the same results. So for the bar plot, you can use the position stake, which will stake the bars together for each of the x values. And if you want to normalize it to be 1, you can use the position fill. And if you want to put the bars side by side instead of stack them together, you can use the position dot. So if you don't want to do anything about the overlapping, you simply specify the position identity. But usually this, I think this is the default behavior. After the position adjustment, we also learn the scales. Basically, the scales tells us how we want to map the values with the aesthetic values. So for example, here, just using the pH value as a representative. So basically in the aesthetic mapping, we map the pH with the color, right? So this will do some mapping, but we still want to specify, okay, in the pH 1, we want it to be red, and in the pH to be 13, we want it to be blue. And so in the middle, we want some kind of gradient. So the color 1 to red and also 13 to blue. This mapping are defined using the scale. And the scale, if we want to set the scale, we simply just need to use the syntax showing here, scale with some aesthetic properties, and also the type of your variables. The aesthetic properties can be position, like X and Y, the color, fill, etc., etc. So basically, the aesthetic properties we introduce in the aesthetic mapping, you can directly use them. And for the type, we usually use the continuous, discrete, etc. So here, just using the X as an example, scale X continuous. So basically, this function has a lot of arguments, such as the name, which stands for the X-axis label, the title, and the limits stands for how we want to plot the range of the X, and the breaks, how we want to show the break of the X-axis and the labels, etc. So basically, this one will help us to customize how we want to show the X-axis. And for the rest of the part, we use the fill as an example that tries to map a color to the field object. So basically for the scale file gradient, we will produce a 2-color gradient from the low to high. Basically, this is like unidirectional. And if we use the gradient 2, we are going to produce a 3-color gradient. Like we have a midpoint, and it usually used to be some kind of diverging colors. So later in the theme, we are going to talk about this in detail. And if we want to specify multiple color gradient, we can use a gradient n. And if we want to specify, so these 3 gradients are used for the continuous variables. We have a transition from low to high, and it's a continuous change. But if we want to use for the discrete values, we can use a scale fill brewer. So basically, this will produce a color palette for the discrete variables. And if we want to manually set them, we can use the scale fill menu. This will try to define a manual color palette for the discrete variables. So yesterday, we also talked about the facet, which tries to split our data into different sub-data. And for each of the sub-data, we make the plot, and this will form a series of panels. And we can actually use these 3 functions to wrap our panels. For example, if we use the facet now, it will not do any faceting. So it's just produce a single plot, which is the default. And if we use a facet wrap, it will wrap our panels into 2D based on the row or based on the column. So basically this function will have some parameters like a number of columns, number of rows that you can try to adjust. And for the facet grid, you can generate a 2D grid of panels, specify 2 variables, like the rows and the columns. So basically for each of the panel inside, for example, take an example here as 1 and A. So it will take the subset of data that has one variable to be the value of A and another variable's value to be 1. So just take that subset data and then make the plot. So this facility is used for the discrete variables like A, B, C. We know it's discrete. So if you are dealing with some continuous variable, you have to do some kind of discretization by yourself. So last part about yesterday is we learned the coordinate systems, specifically the Cartesian, the usual, usually we use the coordinates and also some polar or the nocturne, those nonlinear coordinate system. So for the Cartesian, we can set the limit, like we want to zoom into a particular region of the plot. You simply use the X limit or Y limit and specify the range. Over there, it will zoom into the plot and only show that plot. And we can also try to make some modifications on the scales using the coordinate fixed ratio. So if we set the ratio to be 1, then 1 unit length of X and 1 unit of length of Y, they will have the equal scales. But you can also adjust this ratio to be something else. You can flip the X and Y using the coordinate flip. You can apply some kind of transformation to the axis coordinates. For example, coordinated you specify X to be nocturne. It will give you a nocturne transformation on the plot. And also you can use the coordinate polar to convert from the Cartesian coordinates, which is the default, to some polar coordinates. So yesterday we actually show this little example that for the stacked bar plot, we can utilize the coordinate polar to make it transform it into the pie plot by simply just collecting the head and the tail of the y-axis. So basically, you will see this will form a loop, and then all the other areas will naturally force into this circle, and each of the stacked bar region will become a region in the circle. So this will give us a pie plot. So I think we have already done a lot of things, learned a lot of things like how to make the plot. And the last part is about customization. So basically here in the right panel figure, what we did previously is to finish the first and the second step. So basically we are capable to generate some kind of plots that probably will be useful. And for the next part is that we can add some labels and the titles to the plot to make the plot more informative. Like you denote what is X and what is Y, and you have some titles about the figure itself. So you add some descriptions to the figure. And the next part is about adjusting the themes. And so the final 2 layers is actually we are trying to customize the figures in our desired way. And I think this is really important because with some kind of customization, you actually feel you are very powerful. You have control over everything. So this is give us some kind of a power sense. So for the first part is about the title, axis, and the legend. Specifically for the plot title, we can use naps or GG title to change the title. So if you're using the naps, specify the title or subtitle, and the captions, and also the tag. So this is pretty useful. If you want to generate publication ready figures, you don't really need to use PowerPoint or Adobe Illustrator or Photoshop to make those changes. You can simply just use one single line of code to edit them. So this is sometimes quite useful. And besides that, you can use the ggtitle, and this ggtitle will give you two options. One is the title of the plot and also the subtitle. So specifically, you can also specify X and Y in the naps. So this will change the axis title, X and Y here. But I didn't specifically list it here. So for the axis title and also the legend, we can actually change the label what the title using the scale X continuous by specifying the name, which is what we learned yesterday. And specifically, we can also use the XNAP or YNAP to change the labels of different axes. And another way is that we talk it just allow, we can use the NAP specifying X and Y. So this will also change the name. And to remove the axis label, we can simply assign them with empty string, or we simply assign with the null string. So basically, these two will remove the MPG or WT in this plot. So here comes a question, like what's the difference between these two removal approaches? They are doing the similar job, but they have some difference there. So anyone have any idea about the difference between them?
One change the space and the other elements of the graph.
Right. So yeah, that's a very good point. So basically, the maps X equals empty string. It will preserve the space. It's just like it's empty, so there is nothing shown. But if you specify it to be null, so the space will not even be assigned. So this is the direct difference. Later in the R Markdown file, we will see how big the difference is. So here on the right panel, we have this figure actually shows the different structure, like for the figure, like what's the name of different components. So here, when we talk about the axis labels, we specifically are talking about this, and for this is our axis. And for the legend, this is the legend title, this is the legend key, and this is the legend key label. So basically, I think those figures are sometimes really useful because sometimes you want to change a part about the figure, but you simply cannot name it. Like you don't know how to search. So this is the way. This is a major. I still think this is the major difficulty of plot customization. You know what you want to change, but you just cannot name it. So for changing the axis labels or the legend title, you simply use the name argument, and for others like the ticks or the key labels, you simply specify the breaks and the labels. Later we will in the R Markdown practice we will show them. So this legend can display multiple aesthetics. For example, sometimes we specify the color. Sometimes we specify the shape. So basically, when you specify the color, you will have this different legend denoting like a different color denoting what values. And you can actually so by default it will show up, and you can reduce try to repress them, prevent them to show up by specifying the show legend to be false in each of the layers. And specifically, if you specify the same variable to different aesthetic variables, for example, you specify the shape to be Z and the color to be Z. So in the end, you will see those legends will be combined if the same variable is mapped to different aesthetics. So here is just like 3 different examples here. In the first one, we specify color to be Z, and in the second, we specify the shape. And in the third one, we see that the color and the shape is actually combined together to simplify the legend. And for the legend key, we have the glyphs. So basically, it shows like what symbols we want to use for the legend keys. So this is the right panel actually shows what's available for this argument. The appline, if you are using the line plot, appline and the time series smooth, and if you are using the dot, you can specify either by the point or dot plot. So if you are using the different box plot or bar plot rectangular, you can use those regions. So this is sometimes useful because when we try to plot a geom line, for example, in this figure, this will show a straight line. And if you specify the time series, it will show some kind of a zigzag line. So this is just simply for the beauty of the figures. You actually can change the symbols, not just using the line. Although we are showing a line, but this zigzag line is more appropriate for the line figure here because we didn't show it. We didn't see the straight line. They are like have different ups and downs in the figure. And sometimes we want to specify, for example, the title of the legend. And also we want to specify the key labels in the legend. So basically we can use the scale. If you still remember the scale with the aesthetics discrete, which is a type, you can specify the labels to be the key label, and you can use the name parameter to specify the title of the legend. For example, here we simply change the legend labels from 468 to ABC and change the legend title to be my title. So this is how we can achieve it, how to control the legend title and labels. So besides that, we can use the guide legend to do some additional control over the details. For example, you can control the legend case layout. So by default, it will use the vertical lineup, but you can specify using the guide legend color to be like try to make it into 2 columns. So right now it will just have 1 column. So after you specify the n column to be 2, it will have 2 columns. And you can specify you want to arrange the labels by row, like ABC, or by column or by the row. So the default is like by column A, B, and then C. But you can also specify in another way. First, like if we specify it to be by row, then it will first fill the rows A, B, and then fill the second row at C. So you can also use the reverse argument to reverse the order of the keys. Simply here is just like a reverse of the previous one from the C to B to A. So this is how you can adjust the order, like the appearance order of your key labels. So besides that, sometimes when we are plotting the scatter plot, if the data points is the number of data points is too big, too large, then usually we adjust the transparency of the plot, of the scatter plot. So basically after you specify the alpha to be some value between 0 and 1, you will see the lightness of the color will decrease. So as a result, in the legend, you will also see the color becomes faded away. So if you want to prevent this behavior happening in the legend, you can actually use the override AES and then reset the transparency in the legend. So after you do this, you will see that the legend we see from the left panel and the right panel, it's actually different. In the right panel, the alpha will be override by 1. So we see like exact red and blue and green. So this is another small trick you can use when you plot the scatter plot and specify the alpha. And for those are for the discrete values, and for the continuous value, we have the color bar. Specifically, when you are plotting a heat map or something, you can also control the shape of the color bar by specify the bar width and bar height. And you can also try to specify how you want to present the color, like from the dark to light, or just like do a reverse of the plotting, place them in a reverse order. So here is just like trying to show two examples, like you do the reverse, and or even you try to adjust the bar height, and on your end you can also try to adjust other parameters, like the bar width or the number of beams. So I think we can do some practice by checking the GitHub. Let me see. We can copy and paste this code to our terminal. So if you already have a QC bio data visualization folder, you can first try to remove it. No. And then paste the code here. You will try to clone the code. And after that, you can open your RStudio and navigate to the QC bio folder. In the day3, we will see the markdown file. Right, so let me first clean the environment a little bit. So this is our day3. I think I didn't change the date here, but anyway. So for the first part, let's just load the library and also load the data we are going to work on. So here we're still going to work on the MPG mail per gallon data. So because it's kind of a simple data, we don't need to worry about the data cleansing part, just using this data frame and do some demo on our end. So first, let's create a base plot which only have the data. So we don't specify any aesthetic mappings. We don't specify the geometry in the base. And then for the next data, like plot 1, we try to visualize the data using the scatter plot by using displacement at x-axis and the highway mileage at the y-axis. So after that, let's see what does it look like. So basically, we also use a set variable drive, four-wheel drive, forward or rear drive. So just using them to be the color. So the first part is about we want to change the title of the plot. So here, as we mentioned, we can use the naps to do this, like specify the title, subtitle, caption, and the tag. So if you run that, you will see the title, subtitle, and the caption is changed, and also there is a tag attached to each of the figure. And I think we can do some exercise. Maybe I can give you 3 minutes to finish this 2 exercise. So to solve this 2 exercise, we simply can just add the additional scale. Because, for example, for the x, we have the scale x because right now the x is a continuous variable. So we use a scale x continuous and simply specify the name to be something else. For example, here we just specify it to be x. And for the y, it's similar. Just simply change X to Y, and then we should be able to change the title of the axis from the original like displacement highway to the X and Y. And if we are going to use the map, we similarly can use the maps, specify the X and Y inside. So this will give us the same results. And for the second axis, we actually are testing what's the difference between the empty string and also the null. So if we run it, let me see if I can run it to the IDE. So the results will show like this. So apparently, like for the first one, which is the empty string, we see there is a space, like the spacing is bigger than the second one. Just like try to see like what's the length between the x-axis to the lower boundary, and we see that the empty string has a bigger spacing. So this is the difference between these two plots. That if we use the empty string, it will preserve the space. If we use a null, then the space is not going to be allocated. So if you really want to have your plot to be compact, probably you can try to specify the X and Y to be null. So next, let's continue to learn some legend. So here, for the legend title and labels, just as the slides denoted, we can try to adjust them. So probably we can see what's the original figure look like. Part one. So now the legend title is drive, and the labels, the key labels is for FR. So if we want to change it to something we define, for example, the legend title to be name, to be type, and then for the labels, we want a full name. So we can use the scale color discrete by specifying the name and labels to do this. So after running it, we will see the results that the legend is legend title and the labels will change it to the pre-specified values. So here is another axis. Maybe we can also work on that. I will give 2 minutes to finish it. So for this exercise, we can simply use the plot, and because we want to assign some colors, so we can use a scale color menu. So here we simply assign the values to be red and blue and green. So if you so this is just one way to assign the values. You can also use a named vector, like you want to assign 4 to be red, or F to be blue, and R to be green. So basically, you can use the named vector to do that. So here I just use the like a direct use the vector. So also you want to rename X and Y axis label to be displacement and highway. So we can use the maps and specify X and specify the Y highway. And also specify the title to be, for example, my title, and the subtitle to be my subtitle. So after that, you will see the color is changed from the original color to red, blue, and green, and also there is the title and the subtitle change. So next part is about the legend compound. Yeah. So you mean like you want to change the text, the label? Um, yeah, maybe yeah, I don't quite get the point right now. So maybe later after when we have a break, I can walk to you and then we talk about the plots in more detail. So after that, we move on to the compound legend that we have said before, that when we map the same variable to different aesthetics like color and shape, it actually will match the legend to be just a one single legend. Like for example, here we have the label, the K label to be the red, green, blue, but also have the shape like to be circle, triangular, and square. So this is just a demonstration about the combined legend. So if you want to hide the legend, you can specify the show legend within each layer. For example, in this geometry point layer, you can set the show legend to be false. So this will tries to plot give you a plot without any legend. So again, in the slides, we talk about you can actually control the legend key layout by specifying the guides. For example, you want to specify the color legend to be encode to have two columns. You simply use the guide legend function with n column to be set to be 2. And also you can try to adjust whether you want to fill the legend keys by row or you want to reverse the whole thing. So here we can actually see the results. Like for the original one, we have the only one column, and if you specify the n row to be 2, this will give you 2 columns. And if you specify by row, then this will give you like first using the default is using column for F and R, and if you specify to be by row, then it will fill the legend case in the row fashion, like for F as the first row and R as the second row. So if you want to reverse the whole thing, you can specify the reverse to be true. It will fill the R first. So this last example about legend is the override. We talk about when you have a lot of data point, you probably sometimes want to specify the alpha to be some value between 0 and 1. And the 0 means the transparency is the biggest. 1 is we don't have that much transparency. So basically, after you run it, we can actually see the results for the first figure. You see the dots. They have the lightness of the dots is decreased because we set the alpha to be 0.2, which is quite a small value. And you still see some kind of dark color in the region. This is because we have multiple points. So when they overlap together, then this color will become thicker. But again, like in the legend, we still see the color to be very light. Sometimes we don't want it because we really want to present the original color, and the alpha setting is just trying to deal with the overlap parting. So you can actually try to overwrite the original aesthetic mapping. For example, override the AES list alpha to be 1. So this will change the color or the alpha in the legend. So basically here, the second plot that we shown here, compared to the first one, this will display the whole color instead of the transparent color. Okay, I think we can take a short break here, like a 10-minute break, and then when we come back, we will resume to study the same function. So after the legend exercise, I think we can resume to continue our learning for the final part about the same. So the same is, as we said, it's a non-data inc. So it basically tries to adjust how you want to make some modification about the text, like if you want to use the different font family or font size, etc., etc. So here, if you want to use, there are basically four major components in the same system. One is the same elements, specify the non-data elements you can control, and then there is a same element function, and also the same function. Basically, you will put the same elements equals to some element function within the same function. So this is how you do the control. And then there is also in ggplot, they also provide some complete themes. Basically, they have a whole set of themes you can directly use. Later we'll see them. So here we show the 9 different built-in themes in ggplot2. So specifically, you can simply just using the add function, add and adding this built-in theme to them. So here, the 9 is like the black and white, which is usually typical used. So the same gray is like the default theme in ggplot2. And sometimes we don't want to have those gray lines. We only want to have the very basic X and Y axis. So this same classic is going to be useful. And if you don't want any like themes, for example, you don't want to have a label, you don't want to have the X, Y axis, you can choose the theme void. So basically this will not give you the predefined theme. And if you can actually, so sometimes when you have a lot of theme to be plot, you have a lot of plot and you want to change all of them just in one step. You don't want to specify the same black and white for each plot. You can use the theme set function to do that. So basically, after you run the theme set with this predefined theme, so all the following plots will have the same setting. Like they will automatically have this add and the same black white to all the plots. So this one is saving you some time for the typing. So for the same, this is for the built-in themes, like the complete themes. And if you want to adjust the single components in the same elements, so here is the name for each of the component. So basically here, for the same for the element functions, we have the element text, line, and the rectangular, and also the blank. So these are what we are going to learn next in the next few slides. Basically, the syntax is that you have the same function outside, and then you have the name and the value pairs. So the element name is what we shown here. That for the axis, we have the axis text, title, text, and the line. So basically, here the text we know it's a line type, and the title text and those are what the element text. So basically, each of the function here. Element function, they have the different arguments. For example, if you want to adjust the size of the axis title, you can specify the size within this function. And also, sometimes we want to rotate the labels to some degree, like 90 degrees or 45 degrees. You can also specify the angles within the element text. So besides this X element, there are also some other elements about the plot, like the background of the plot, which is shown in the yellow here, and the title of the plot and the margin of the plots. So if we are working with the facetting, then there are also some other elements like the stripe background. Here it's black. So basically, you can also change it to be white or any other color you want. And also the spacing between the panels and the text of each of the panels. So again, these are the basic types like the element text. So for the legend element, you can also change it, like the margin, title, and key, and also some other key labels, text, and the legend background. So also you can decide the legend position using the same function. So for each of the panels, you can also fine control it by specifying the background. Here is the light blue, so you can specify it to be, for example, the white color. And for each of the horizontal line and the vertical line, those are the grid lines. You can also control them using the panel grid. For example, you want them to disappear, you can actually just use the element blank, assign it to the panel grid. And also the panel border, which will define the border lines, the border lines thickness, the border lines color, etc. So basically, this is the whole details about the different components about same elements. Again, like if you don't see this figure before, and if you want to change a particular part, the most difficult thing is how to name it. Like when you go to Google or something, you don't know what you want to search. So this is the most difficult thing. But using this figure, you probably can locate the answers more easily. So for the modifying the same components, as we said in this ggplot2 same elements, you simply use the same function and assign the element function to the element name. It's a name and value pair. So for the element function, there are 4 basic types. For example, if you want to do anything about the text, you use the element text. Do anything about the line, you use the element line. And if you want to do a region, you're using the rectangular. And if you simply want this element to disappear, then use the element blank. So the blank will try to hide the element for you. So for the element text, it will try to draw the labels and the headings. So anything that is related to a text, you can use it to change. So it will take arguments like the font family and the font face. So especially sometimes we want to highlight something, you probably want to change the face to be the bold font or italic or something else. And you can also try to change the color, size, and the H-just, V-just, and angle. So for the H-just and V-just, so basically it's in the right panel here, the H-just just means the horizontal adjust, and the V-just is a vertical, like V stands for the vertical. So if it takes the value of 0, it means the left adjust, and if you take the value of 1, it means the right adjust. And if it's 0.5, then it's the center. So we can just take a look at the V-just and H-just to be 0.5. So the point and the labels, we can see that the text label is just a center at this point. And if you adjust the H-just and keep the V-just unchanged, so you can see whether the text is left aligned or right aligned. And if you want to adjust like the V-just, you can see whether it aligns to the top or aligns to the bottom. So this is a simple demonstration of how to use the H-just and the V-just. And for the angles here, you can simply adjust the orientation of the text. For example, here, every angle here showing like 45 degrees. And then if you want to put it into vertical, you simply specify the angles to be 90s. So I think most of the time, this angle or the adjust is useful. For example, when you have a box plot or bar plot, and your x-axis has a lot of values, and then the values probably will overlap with each other if you don't specify the angles. So sometimes you want to rotate a little bit, so still you can see the text very clear, and probably that's when you need to use the angle argument. So here it's just a simple demonstration about how to use the function. Simply, for example, if you want to change the plot title, just use the plot title equals the element text, and you specify the face to be bold. You want to give it a red color and adjust the size. So it's pretty easy to use. And sometimes we want to control the margins around the text. Still, using the plot title, you can specify the margin to be something like you specify the top, bottom, right, and left. Just specify how much space you want to keep around this text. So you can use the margin function to do it. That's a good point. I actually didn't check it very carefully, but I think you can just put a question mark of and then put a margin, and then you will see whether it's in the pixels or in the inches, etc. So I didn't check it very carefully, but I think using the ARM Studio, you can find it out easily. So that is about the text. And if you want to change the line, you can use the element line to do that. So basically the line, it also can take the value of color, size, and the different line type. So here it's that we can change the major grid line to be the black color, and we see the major grid line is black, and the minor grid line will still be the default value. And we can also change the line, the size, like the line wise. And also we can change the line type to be dashed line, dotted line, etc. So this enables to this element line function enable us to change the appearance of the lines. And for the element rectangular, it tries to draw rectangles, mostly used for adjusting the backgrounds. For example, the plot background or the panel background, or even when we are using the faceting system, we can change the stripe background. So basically here, you can specify the file to adjust the color of the background, and you can change the border line, like a color or even the border thickness of the element. And also you can change the line type of the element borders. So here is a small demonstration about using it to change the plot background. For example, we use a fill gray to be specify them to be the gray, and using the color to be NA. So basically the fill and the color, one is controlling how we want to fill the whole area, and the color is controlling how we want the border lines to be colors. So basically the color equals to NA, that means we don't have a border line showing up. And we can also change the color to be red. So basically this will only have the border line to be the red. The interior is controlled by the fill. So basically that one isn't changed. And we can also fill it with another color. So this is about the element rectangular. We can use it to change the background of different elements. For the element blank, draws nothing. So if you want to hide something, you can use it. So for example, here, we can hide the minor grid line, which is a more thin line here. So if we put the element blank, we will make it disappear. And if we use both of them to be blank, then we will not see any kind of grid lines in the plot. So here, we still have this little difference by specifying the color to be NA or just specifying the whole element blank. So for example, here, if we specify the color to be NA, it will create some invisible elements. So that means the space will be reserved. But if you specify the whole thing to be element blank, so this will not draw anything. So there is no extra space is allocated for that element. So this is still another way we like it's another example we seen before. Like when you specify the X labels to be empty string or the null value, so they have a space difference. Here we also have this spacing difference. So there is another function about the same update that once you modify your themes, you probably want to use it for your rest of the plots. So you can actually use the same update to make it happen for all the plots of all the following plots. And this same update will return the current setting. So when you run it, it will have the same settings as a return value. So basically you can assign it to a new variable, and you make all your plots there. And after you finish everything, you can sim set the older sims, like you reset the same settings back, and then try to use the original sims for another plot. So this one will enable you to do some kind of flexible coding. So you don't need to set the same for every plot within the for every plot, and then you can revert back to the older sims by just specifying the sim set to be the older sims. So all right, I think we can move on to the practice example about the sims in the R Markdown file. So for the first one, basically for the sim elements, as we mentioned, we can adjust the text of the line and the rectangular. So for the first one, we can directly adjust the axis title. Let me see. Let me see the original plot one. It's shown like this. Actually, run. Not sure why it has a strange error on this computer. On my Windows, it's working fine. But anyway, the major idea here is that you can try to adjust the elements. You specify the name and using the element text to element text and specify each of the attributes there. I think probably it's a function. Yeah, that's a point. Yeah. So basically, if you are using Mac, probably you don't have this font. So, but yeah, let's just remove it and see whether the axis title is changed to the bold font. And so compared to the original value, which is the default, and then we adjust the face and also the size, we can clearly see the text title is changed, is updated. So that is for the text, and for the line, we can try to use the panel grid. For example, we want to change the panel grid, which is like the grid in the plot. So we can use the element line to specify the color, or even making them disappear by using the element blank. So let's just see the plots. So this is our original plot. And if we want to specify the element grid, like what the major and the minor grid to be the gray value, to have the gray color, then we see compared to the previous one, the white line, now we have all the grids to be gray. And we can also make the grids disappear, grid line disappear by using the element blank. So this will try to not draw any lines, draw any grid lines. So compared to the original one, we don't see those horizontal and vertical lines anymore. So the next part is about the rectangular to adjust the panel background. So here, if we run it and specify it to be different color, so here the plot color means everything in the plot, and the panel usually only means the region that within the X and Y axis. So this is a slight difference about the plot and the panel background. So but anyway, you can choose to change the color by using the fill argument within the element rectangular. So compared to the previous one, you can see the color is changed. So maybe we can go back to our slides about the figure saving. So basically, after you generate the figures, you modify the themes, you customize as you desire. The next part is about to save the plots into a file so that you can use it in your manuscript, in your paper, etc. So here there are two different figure formats. One is the vector graphics that tries to describe the plot as a sequence of operations. For example, it will describe, we want to draw a line from one coordinate to another coordinate. We want to draw a circle. So this vector writes the graphics because it only records the sequence of operations. So it will have no issue for the zoom in. So basically you can zoom in, like you don't lose any resolution when you zoom in. So the widely used vector graphic format are the PDF file or the SVG file. And besides that, we have also another like raster graphics, which will store the plot as the array of pixels. So basically this will have the fixed size of pixels, like n by n dimension, etc. So when you zoom in, it will have some kind of resolution issues. So basically, when you zoom in, probably in the vectorized format, because it only records the operations. So when you zoom in, it still shows as a cycle. But if you just discretize the figure into pixels, when you zoom in, you probably will see those kind of like blur edges. And for the raster graphics, the widely used one are the PNG or JPG or JPEG, etc. So these are like based on the extension of the file, we can actually tell whether it's a vectorized graphic or the raster graphics. So usually we will prefer the vector format because it will not lose any resolution, and but usually we will choose the vectorized format, like save the plots into a PDF format, unless there is a compelling reason not to do that. For example, some website probably will ask you only upload the PNG file. So when the format, we have a restriction on the format, then you use the raster graphics. And another thing is about the speed and the size consideration. So basically, because the vectorized format, they record every operations in the plot. So when you, for example, when you have a lot of points in the plot, for example, like in the genetics, you plot the Manhattan plot, you have probably tens of thousands or even millions of points over there. So when you make the Manhattan plot or scatter plot in that situation, the vector format will take a lot of space to be saved. And also it takes quite a long time to really render the figure. So in that sense, we will switch to the raster format because it only preserves n by n pixels. So that one is much more memory efficient and much easier to make the plot. So if you want to save the plot2 file, you can choose several options. Here, like the base R provides a PDF function or PNG function that tries to save the plot to a PDF file or PNG file. So this is a standard approach in the R in the base R environment. So basically, you will open a graphic device and generate the plot and then close the device. So the device here is simply the file you are going to write the plot to. So here is like the syntax about using the PDF. You specify the file name and you specify the dimension of the files. And then you make the plots within the device, and then after you finish, you call the device off. So basically, this function will give you will generate a figure in the path you specified. So besides this PDF function, if you use ggplot2 and then want to use a ggplot2 to save the figures for you, you can use the ggsave. So basically, it will save the ggplot function object to your file. You can simply just use the ggsave and specify the path, the file path, and then specify the plot. So it will automatically decide what kind of figures you want to generate by the extension. So for example, if you specify the .pdf, it will automatically select using the PDF version, like a PDF format for you. And if you specify the PNG, then it will use the raster format for you. And for the ggsave, it takes several parameters. The usually used ones are the width and the height. And if you save it into a PNG file, you can specify the resolution by using the DPI. And this plot actually is optional. You don't need to specify the plot object. If you don't specify them, it will automatically save the master plot into the file. So this is sometimes quite useful that you can just first make a plot and show it, and then just using call ggsave and use the file path, and then the plot will automatically be saved. So I think we can again move on to the R Markdown, and here are two exercises you can try. Maybe I can give you guys 2 minutes or 3 minutes to finish the exercise. So for the first exercise is that we want to increase the size and the of the legend key and the labels. So the legend key, we can use the because the legend key, if you simply go to the R Markdown and the plot class C legend key. So basically, it will have some kind of prompt and notify you what kind of elements they are. So for here, the legend key is an element rectangular. So basically, you can specify the size within the rectangular. Like for example, here you specify it to be 10 or 15. And for the legend labels, you can specify it by the text. So element text, sorry. And then size should be again 15. So after running it, I think for the key size, you can increase it bigger. So here the element legend key will only change the spacing here, I guess. So if you find out how to change the dot within the legend, please let me know. So right now, I think it's fine because we only change the legend key, just specifying the size within the element rectangular. So after that, you can use the ggSave to solve the second question that tries to save it to the PDF. So this will, because we don't specify the plot object within the ggSave, it will automatically save the master plot in the device. And we can see whether the results has been saved. So here it's a file we just created, the plot PDF, which contains the plot. And also it's in the PDF format and automatically saved as the PDF vectorized version. So I guess we can take another 10-minute break, and then after we come back, we finish the rest of the materials. So before we move on to the new contents, I will still want to revisit this exercise a little bit. So previously we set the legend key, for example here, to be something else. But we didn't really see the key size is changing. So an alternative way, like a workaround way to do that, is by specifying the specifically working on the legend itself, not on the sim itself. So for example, previously we know that we can use the guide to override some of the settings. So for example, the guide equals to let me go to the slides a little bit about the guide itself. So basically, previously when we see that we can use the override AES to adjust some properties. For example, here we adjust the alpha, and if we want to adjust the legend, the symbol size, so we can use the guide. Let's see, guidelines. Guide legend. So override AES and specify the list of size to be something. Let's see. Could be guys. So right now the symbol size will change accordingly. So it's not something we can do in the same, but it's if we really care about the legend itself, we should directly modify the legend. So the what?
Color.
Yeah. So because when we make the plots, we use the color, like the legend is actually specified by the color. So when we make the scatter plot, we specify that drive to be the color, and then this legend is specifically for the color properties, and then we want to increase the symbol size, so we can use the color, the guide legend override AES to make it.
Shape, right?
Right, exactly. So, all right, let's go back to our slides and let's finish the rest of this. So far, after we finish the same part, we basically finish everything about the ggplot, and the next part is about the general principles about data visualization. So basically, we know that if you have one data set, and there are actually multiple ways to visualize it. So basically, you want to find the most effective way, or even the most efficient way for data visualization. You can actually consider the whole process like an encoding and the decoding process. For example, we encode using the ggplot2 to encode the data into some figure, and then after our humans see the figure, we probably think and extract the information from the figure. That is, we're actually trying to decode the data, decode the figure into some kind of original data. And so basically, our main purpose is that we want to make the decoded data and the encoded original data to be as similar as possible. So it's more like a sense of minimize the risk construction loss. So how to do that? So one thing is that we need to think about the message. Like if you have tons of data, then you need to extract, okay, which part of the data you want the audience to see. So this is just simply try to think about the message you want to convey using the plot. So basically, this is a famous a famous computer scientist, Richard Hamming. So he invented the Hamming distance. That Hamming distance is widely used in modern computers. So he has a book called The Numerical Method in Scientists and Engineers. In the preface of the book, he mentioned the purpose of scientific computing is insight, not just numbers. So it's very similar in our data visualization that the purpose of the plotting is a message, not the different kind of plot files. So the idea here is that we really need to think about the message first, and then we make the data, we make the figures. So to think about the message, if you, as we mentioned previously, if the message is showing relationship between several variables, then we can try to use a scalar plot to show them. And if we want to make a comparison based on the variable types, we can use different visualization like a bar plot or the line plot to show them. If we want to show the distribution, we can use a histogram, density curve, etc. And if we want to show the composition, then using a bar plot or the area plot will be suitable. So based on the message you want to convey, you can actually select the right type of plot that conveys your message most efficiently. So besides that, we actually have a lot of other principles for data visualization. So this is this part of the slides is based on this book for the Introduction to Data Science. So this book is written by quite a big name in the field called Russell, which is a professor at Harvard University, specifically in the biostats department. So in this book, they listed several principles when we do the data visualization. So they give some examples we are going to see soon. Based on the examples, we know we probably can get an idea of how to better visualize our data. So the first thing is to use the appropriate representations. So this is quite critical for example, showing using the two plots here. In the right part and the left panel of the donut plot, we know there are some kind of difference inside, but we don't really know how big is the difference. So instead of using the donut plot to show the difference, we actually can consider using the bar plot to do a side-by-side comparison. So this is because our eyes are really good at judging the linear measurements like the height or the width, but it's really poor judging like the area or judging the angles. So basically, when we want to display some quantities relationships, the positions like X and Y on the scatter plot, and also the length of the bars are preferred over the angles or areas, and even better than like the color brightness. So because some of the people they really don't have a hard time to identify the color brightness. So another thing is that based on your data, different representations have different focus. So this is to echo why we need to use the appropriate representation. So for example, just take the 2020's election as an example. If we just look at the Republic or Democrat for each of the state or each of the city, we probably see the vast majority of United States is in red. It stands for the Republic. This is good to show, okay, which state, which city is a Republic state or etc. But it's not reflecting the whole populations. So basically, because some of the states they have a very large area, but they have a very small or very few people there, small population there. So basically, if we are going to see the how much people voted for the Democrats or the Republic, we actually need to do some kind of normalization that tries to use the use the population as the focus instead of using the area of the state as a focus. So this previous one is just coloring the state, but the later one, we consider the population, like the different circle size, stands for the number of populations in this city. We actually see the blue color is the majority, instead of for the previous area plot, which red is the majority. So basically, these two visualization, they have two different focus. One is focused on the area, one is focused on the population. They represent a very different message here. So besides the representation, we sometimes also need to add some necessary annotations. So for example, for a pie plot, it's usually recommended to add some symbols, try to show what percentage this slice accounts for. So this will give us a more or less quantitative idea. If we just using the angles, we probably don't have a good estimate like what's the proportion of this slice in the whole population. And another example I want to showcase is from like the advertisement of Apple. So basically, they tried to compare their own chips, M1 chip, to other PC chips. So do we have any like idea? Why do you think this one is an effective representation? What's the advantage of this figure? Any idea? Like what do you think? Why this figure? What properties make this figure a good visualization? Yeah, it's unlabeled, but I think it's not a big issue as long as they are on the same scale. You only care about the height, right? You don't really care about the exact values. Yeah, I think it's a CPU performance. Yeah, it's really.
Oh, I can't even see that.
It's really dark.
What's that? I think it's
Yeah. Yeah, X is the power consumption and Y is the CPU performance. So yeah, that's a good observation. So basically, you see that we added some kind of vertical line, horizontal line. So basically, this will give two information that at the same level of power consumption, they achieve a higher performance in CPU. And if they add the horizontal line, they actually give a message that at the same level of CPU performance, they consume less energy. So this makes the data visualization really good. So I have to say, like Apple, like when they really need to advertise something, they put a lot of effort on the data visualization, and it's from here. And another part about this data visualization, I think what is good is that they color the latest PC chip using the gray color, and they color their own product using some some colorful color, like changing colors. So this also have some advantages because we know that gray color is usually stands for something boring, something that is not our focus. But the shiny color really catch our eyes at the very first point. And another good thing about this figure is that they use like a pure black background. So basically, the black they don't use like a gray color. They don't use white colors of the black. It makes the contrast even more apparent. So basically, the black means okay, there is nothing in the background. Our own focus will only be drawn by these curves, not something else. So basically, this is a good example to saying that other necessary annotations can help us better understand the plots and better understand the message. And the next part is about don't misread the reader. So this is like from Fox News. So we can actually see they are plotting two bar plots. And because our eyes are really sensitive to the bar heights. But if you take a closer look at the bar plot, you actually found, okay, the starting point is not from 0, but from 34. So if you are going to plot the whole scale, you will see like the whole scale is from 0 to something 35, etc. So the dramatic difference in the left panel, like it's maybe 3 or 4-fold difference. Here only becomes like a 30% of increase. So this is like the left panel is actually trying to mislead the reader. They are showing, okay, the right bar plot it's way beyond the left bar plot, but instead we only see the difference only 10%, 30%. So basically, the left one is a better example about misleading. The right one is more accurate. So whenever you are using the bar plots, it's a kind of misinformative to not start from the start the bars at 0. And if you are using something else like a box plot, it's okay to not start from the 0 because box plot really care about the distribution between two groups. Sometimes we only care like if the means are different. So in that sense, we don't put that much focus on the height. And another example about misleading the reader is from famous TV series, the Dopesick. I don't know if you guys have watched it or not. So basically, it says like there is a pharmaceutical company. They invented a new drug, and this new drug has some kind of additive effects. So especially for the time from dose, like as the time goes on, if you taken that pain cleanup drug, so basically the concentration of the drug in your blood will increase first and then decrease. So if the drug increase very rapidly, so this will increase the risk of being additive to this drug. So they play some kind of tricks in the data visualization. So basically when they submit the files to the FDA to ask for approval, they play some tricks by utilizing a log10 scale. So making the difference or making the slope looking more, looking less steep. So basically, for example, here, when we have the 4 hours, we actually see probably the difference is like twice, like from 50 to something somewhere between 26, 27 to 50. But in the log10 coordinates, we actually see the difference is not so big. They are really like it's really not steep at all. So this is something like about the misleading part. So whenever you see a bar plot or whenever you see a curve line plot, you always need to check the coordinates, whether this line, the flat line is really flat. So this is just a small suggestion that saying is not believing. So you need to really be skeptical about the plots you read. And another suggestion about the data visualization is to order the categorical by a meaningful value. So for example, in the left panel here, because we are ordering based on the alphabetical orders, like from A to all the way to W for each of the state. So this is a natural behavior in ggplot2, but we can really don't see any good information there because the plot is too chaotic. However, if we order them based on the meta read, we can clearly see the results. Like for example, if we want to know which state has the highest meta read, which state has the lowest meta read, we can get that information very quickly. And another example from here is that from the chaotic part to the organized part, apparently organized part will have more information shown, and the plot will be more clear. When you read the plot, you can instantly get the ideas. And the next one is about to show the data. So using the summary statistics is not enough. Simply, as the example shows here, if we only care about the correlation between two variables, the standard deviation, the mean, etc., all of them are the same in the 4 different panels. But the data is totally different. For the first one, it's a linear relationship. For the second one, it's a nonlinear relationship. And for the fourth one, it's this correlation is purely resulted by some outliers. So it's always suggested to show the data itself. Don't just give like a correlation between two variables, because the correlation is kind of misleading. And so this is another example that, for example, when you see two variables, they don't have correlations. This doesn't really mean they are independent from each other. They probably have some additional patterns. For example, they follow some kind of follow some kind of function pattern, like the circle around, make a circle. So basically, they are not independent with each other, but somehow the linear relationship between them is still is computed as a 0. And from the plot itself, show the data also have some good advantage to make the plots even fancier. So for example, visualizing the distribution is much more informative, just visualizing the mean and the standard deviation. So here, the box plot with some scatter plot will be preferred over the left-hand side bar plot. And sometimes we want to make some comparison. So a good thing is to make the comparison easy. So for example, you probably need to keep the axis the same when you want to compare the data across 2 different plots. And if you want to compare the different data to see the horizontal change, then you probably need to align the plots vertically. So for example, here we have 2 groups, and we care about the mean or median value. Then we probably need to align these 2 plots vertically so that we can directly see the difference in the mean or median. And also, if we want to compare some group together, like you put them closer to each other, will make the comparison more easier. So for example, here we try to compare two time point in the same state. So we can just put them side by side so that we see whether they are going to increase according to the time point. And another good thing about putting them together is that you can actually easily color them. So this will make the comparison much easier. So use a color is a good way to make the comparison. And also, when you use a color, the message probably will be clear. But we also have some kind of suggestions about how to use a color. So for example, we talk about these 2 different color style. One is a sequential color that you have a unidirectional from the light to the dark. And you also have the diverging colors. For example, in the middle is the white, and from the red to the yellow to the blue, or from the red to the white to the blue. So basically, these 2 different color style should be chosen based on your data. For example, if you have a gene expression, then from low to high, you want to use sequential colors. But if you also want to show the change, direction, like you try to compare from 2 groups, some of the genes may be downregulated, and some of the genes may be upregulated. And you really care about the directions and as well as the strengths. Probably you should use the diverging colors. So besides the colors we use here, there are also some other fancy colors. So here I just give an example about Wes Anderson, who is a famous director for the different movies. Right. Yeah, thanks for the comments. But again, like the point here is that we actually have all the options with Wes Anderson. And if you are really curious about what option we have, you can go to this package. So it will actually give you some classic color style than the previous like basic colors. So the colors also means something in theory. For example, it's related to the psychology and also the cognitive science. So for example, the red color usually means like anger, warnings, etc. because it's a color of the red light, right? When we go to the when we drive our car and we must stop when there is a red color. And for the green color, it always means like relaxing. You are permitted to do something. So basically, you should be mindful about when you try to use a color. For example, if you want to alert something, when you make the box plot or the bar plot, you want to alert something, then probably use a red color. And if you want to emphasize some point, use like a shiny color, like the yellow color, orange color. So here is like a two simple example about color usage compared to the left part and the right part. Compare these two parts. Which one do you think you are more willing to buy a product? So, any idea, like buy now, like in the red, or buy now in the green? Which one do you make you have more desire to buy a product? Yeah, the green. So yeah, so as I said, it's very natural because in our daily life we deal with this. Like red is a stop. You need to consider. You should stop and think. And the green is that you are free to go. It gives you more like freedom, etc. So there are a lot of like studies behind the color theory, and I think the advertisement people, they care about this a lot. So probably in our own data visualizations, we probably should also consider how to choose the color that make your figure much more like compelling.
I think a lot of people use the print journals online. It's in print, yellows don't show up there.
Right.
It's a function of reading on things or reading on screen. So this theory is changed a lot depending on whether you think what's doing on a screen or whether.
Yeah, that's true. That's true. And also another part is about the color blindness. So this will also influence the color choice we are going to use. So basically, there are like 8% of male and 0.5% of female. They are colorblind in the world. So really, like you need to, as you said, you need to consider the media of your data visualization process, and also you need to consider the audience of your data visualization. So basically, this really depends on like the specific scenarios you are going to face, and if you are really need to consider the colorblind friendly palette. So here I listed two of them. Basically, these are the safe choice. And you can go to the link I pasted here. Basically, we have a whole page about this section. So finally, that sometimes I notice in a lot of journals that we are pursuing more than two-dimensional plots. For example, the 3D plot showing here. because what we usually do is just plot on a two-dimensional space. So probably it's better to stick with the 2 dimension, not blindly go to the 3 dimension or the pseudo 3-dimensional plots. If you really want to add a set of variable, probably map them to aesthetic properties. So basically, in the right panel, we actually can see it's much clearer than the left panel, because after all, what the data visualization and the plotting, the finish on a 2-dimensional plane. So it's usually a natural choice to stick with the 2 dimensions. And I think we can again move on to the markdown file. So here is 2 practical examples, and for the sake of time, so basically I provided two plots in the D3 folder, and the practical example is just trying to reproduce those plots. But right now, I think we don't have that much of time, so probably you can practice it by yourself. And later, I will post the answers and upload to the GitHub. If you have any questions about how to make it happen, then you can check the GitHub. And I also want to emphasize some useful packages you might need or might use in the future. So one is called the Eclipse. So if you haven't installed it on your computer, you can go to the home page to install it. But what it actually can do is that it will add in to the RStudio. And for the Eclipse, it actually have a ggplot2 builder. And when you open it, it will actually give you an interactive panel that you will select the data frame you want to visualize. After that, you can actually just using your mouse to click. For example, you want to use the displacement as x-axis. You want to have the highway as a y-axis. So basically, it will give you the automatic plotting. You just need to drag something to different columns. You don't need to write the code. So for example, if we fail by the drive, I think drive is the color. Yeah, it will give the exact figure as we did before. So now several panels in this terminal. You can go to the code terminal and copy it. So basically, instead of just visualizing it, you actually can copy the code to your own terminal and then make the modification from there. So it's quite a useful tool that you can do some data exploration first before you writing any code. All right, so this is the Eclipse. And there is also another package called ggplot2. So this is particularly useful when you are trying to visualize the group difference. For example, here I try to use it to plot the group violin plot and try to visualize the difference, like the significance between them, between different groups, try to show the p-values of different groups. So you can use the ggviolin plot, ggviolin function within the ggplot2. And the plot means the ggplot use specifically designed for the publication. So there are a lot of other functions over there, but it's quite useful. You can use it directly instead of building the plot by yourself. You don't need to spend maybe 1 hour to just reinvent the wheel. Just use the function will be pretty convenient. So there is also another package called the ggextra, which will try to show some marginal plots. For example, here we create the original like scatter plot, and we want to show the marginal plot. One idea is that we can use a geometry rug, and then another idea is just use the gg marginal in the ggextra package. So after that, we can see that this is our original figure, and we actually can add the scatter plot, the histogram for each of the marginal variables, like how they distributed. So this is sometimes useful when you do some diagnostics. You want to see whether your data follows some kind of assumption, like they are coming from the standard Gaussian, or they are coming from another distribution. So this is pretty helpful to realize the distributions. So after you have a lot of plots, you sometimes want to combine them just using the code instead of using the PowerPoint or Adobe Photoshop, etc. You can actually using the patchwork to do the combination for yourself. So basically, you have those plot, finish the plotting, and then you can try to put them side by side by just combining them using a plus sign, or you want to plot them like one is at the top, one is at the bottom. Then you can use this vertical line. So if we run this code, we can actually see the results. So for the first one, these two plots, P1, P2, they are placed side by side. So this forms a panel. And if you first combine them side by side, and then put them one at the top and one at the bottom, so you can actually create different panels of the combined plots. So there are also other useful functions I don't have time to introduce, but I pasted a link. For example, the ggplot tries to plot the correlations. ggridge tries to plot the ridge plot for visualizing the distribution. And the ggsci provides a lot of good things. And ggbreak tries to plot some kind of axis breaks for you. So there are also other extensions I didn't list here. You can check this website. But basically everything every plot is started with the GG. So it's a kind of like a specific theme in the R data visualization part. So if you are really like a nerd in the R data visualization, so when you see some image, you actually can wonder, okay, maybe this is generated by some GG sunshine, GG mountain, GG grass, etc. So you actually have a lot of thinking about our daily life. When you see like an object in the daily life, you see, okay, this is a GG table, this is a GG chair, etc. So basically, it's just a simple meme in this R data visualization world. So all right, I think we finished all the coding materials here. And if you have any questions, where to get help. So here I listed several useful links, like the in the R community, ggplot2, they have specific channels. You can ask a question there, and some ingenious people will help you. And the R graph gallery, they contain several plot templates. You can directly copy and paste. And when you don't know the usage of about specific functions, you can always Google and Stack Overflow. And also the last thing I want to emphasize is that the ChatGPT is really powerful in helping you do those jobs. So specifically, there is one option you can use it to upload a figure to it. So for example, here I just upload the figure, example figure. Ask the ChatGPT, please write the ggplot2 code to generate the example figure. So basically, it will try to make the plot in Python because it has a backend Python running console. But instead of besides that, it also generates the code for you, and the code actually is working, is functional. And you can actually after ChatGPT give you the code, it probably will not generate the exact same figure as your original figure, but you can always modify the code template and then to make it closer. So this is really helpful and really increase your productivity. So I think that's everything for our our workshop, and this figure is also generated by ChatGPT. I was saying like I was teaching a data validation workshop. So please make a figure to wish the audience good luck and have fun with ggplot. So this is the result. So I think it's really revolutionizing how we work. Previously, if we don't have the ggplot2, we don't have the ChatGPT, you probably need to write every line of code by yourself. Right now, you can actually reduce the plotting time to a large scale. So I highly recommend you guys try to use it and then make it to increase your efficiency, work efficiency. So I think recently the CEO of NVIDIA said something like the ChatGPT is enable everyone to be a programmer. So basically, it will like in his opinion, like the most promising major it's not computer science anymore because everyone can program. So basically, it lowers the bars. So yeah, but I don't know, like for example, in the 10 years, do we really need to have this many programmers? I think probably not. The ChatGPT can finish most of the work. But in the other way, like we can move our focus to something less trivial. Like for example, you probably can put more focus on the source, on how to make something happen, like the general blueprint, and leave the implementation details to ChatGPT. Probably that's a good answer. So anyway, I think we finished the workshop. The homework will be released on the weekend, and there will be another email sent to your inbox. So please take a look at your inbox on the weekend. And the homework will be due in 2 weeks, so you will have plenty of time to work on that. And it's totally okay to use ChatGPT. So probably you will only spend 1 hour to finish the homework. All right. If you have any questions, I will stay here for another 10 minutes. If you don't have questions, you are free to go. And good luck and have fun with ggplot2.